All right, so let's get started. So last time, well, we've started function spaces. That's the next unit of content. So CTS XY is the set of all continuous maps from X to Y, X and Y topological spaces. I sketched, in some very brief way last lecture, why function spaces appear, at least, say in physics or applied mathematics. This was an example, right? I was discussing configurations of, well, first of all, a particle in space, so that's just a list of numbers giving its coordinates, or say its momenta, if you're talking about phase space as well. But the sort of position configuration of a string, say, is a continuous map from 0, 1 to R. And then we discussed, well, if you wanted to talk about the time evolution of a string, it seemed like there was two ways of doing it. You could either say, well, the time evolution of a piece of string is given by a function which attaches to the time and the position between 0 and 1, let's say height above I at time t. That's reasonable. But if we want to talk about configuration spaces in a serious way, then, well, certainly we must. If we can't talk about configuration space for a string, then we're not going to get very far with anything more interesting than that. So it makes sense that we'd want to be able to put some sort of topology, at least, or maybe even a metric, on the set of configurations of a string. And then we could reasonably talk about continuous maps from R, representing time, into that configuration space. That would be another possible meaning of the time evolution of the configuration of a piece of string. And, well, those two ought to be the same, perhaps, we think. So that's where we finished last time. So today's lecture is, well, I'm going to define this topology, or at least build up to it. Okay, you thought Sierpinski space was just this loser topological space, so it's just there for counterexamples. No. All right, but before I get into the glories of Sierpinski space, well, let me maybe make the point in a more fine way about why we care about function spaces. Well, why do you care about space at all, say R or C? Why did people invent R? Why did people invent C? Well, that's where solutions of equations live. That's the whole point. Right? Literally in the case of C, you invent that so that there's a solution to a particular equation. Well, function spaces, let's say, that's the case we've talked about, right? The configuration of a piece of string, or we could have complex valued functions on a space. That would be the example of a function space relevant to quantum mechanics. Of course, that's a large focus of the end part of the course on Hilbert spaces. Or more general function spaces. So, for instance, the relevant dynamical quantity in general relativity is a metric tensor, which is a continuous map taking values in a space of inner products. That was the whole point of the tutorial on Sylvester's law of inertia. We're coming back to that at some point. Okay, so general relativity and more generally quantum field theory are about taking more complicated spaces Y. Those give the relevant dynamical quantities in those theories. Okay, so, well, those sorts of spaces are where solutions of differential equations live. Right? That's why we care. Well, I care because there's beautiful theorems. I'm a pure mathematician, but okay. So maybe you care because it's where differential equations have their solutions. Typically, of course, the solution to a differential equation might be not just continuous, but smooth in some sense. So there's various refinements of these sorts of spaces involved. but this is the basic level. Well, you might say, okay, fine, I accept that a differential equation, its solution is a function, and it probably better be continuous if it can be differentiated. All right, so you believe in the sets of solutions, but why do you care about the topology, which I'm claiming exists? Why are you forced to care about these sets of functions, not just as sets, but as spaces? Well, that's because solving differential equations or understanding the set of possible behaviors of a system, which are basically the same thing, that's a hard problem. And understanding the structure of these spaces is, let's say, often the key to understanding the possible behaviors of the system. And a typical example is, symmetries. I don't know if any of you have studied the sort of ground state of the hydrogen atom, and for that you need to pay attention to all sorts of symmetries which aren't necessarily immediately obvious. So understanding the symmetries of a physical system, which ends up telling you something about the symmetries of these spaces, is often the key to understanding a physical system. Okay, so that's a sort of very brief reason why function spaces are everywhere in applied mathematics and physics. And, well, as I said, these sets of solutions to differential equations, which are subspaces here, may have additional structure, but the very bottom, the most basic element of that additional structure is the topology. Okay, so that's our challenge for today, is to put a topology on the set of functions between two topological spaces. Well, let me make a remark which will be relevant. This is an exercise in the notes, exercise L12.1. So if, and this is a third way to think about a continuous function, if you like, which is in terms of its graph. So if I have a continuous map, and if the target of that continuous map is Hausdorff, then the graph, which I'll write with a gamma, so the graph, that's a subset of x cross y. As long as y is Hausdorff and f is continuous, that's a closed subset. And there's actually a converse, as long as y is compact. If the graph is closed, if f was just a function, I could write down the same set. And if x was compact, I could deduce from the graph being closed that f was actually continuous. Okay, so what you should remember is that continuity of a function and the graph being closed are very close to being the same thing. So if I wanted to talk about configurations of string, well, the graph of that would be some closed subset of that Cartesian product, and that's another way of thinking about a configuration, right? So, and you might think, well, if I want to think about the topology on the space of functions, maybe it somehow feels a little easier to think about two graphs being close as closed subsets of the Cartesian product, rather than thinking about two functions being close. What is that supposed to mean? Okay, so this we'll make this precise with a theorem a bit later.
So the setting of a graph, is that not just the set theory definition of the function?
Yeah, that's right. Yeah.
So it is
It's
the same, yeah.
Yeah, that's right. Yeah. Strictly speaking, right, when I write down f, that's what I mean. Yeah.
It's just making that explicit.
But if I said f is continuous if and only if it's a closed set.
Yeah.
All right. Okay, so what's the... And there's a few ways of thinking about the topology on function spaces, but what we're going to take as our guiding principle in deriving the topology is the following identity, if you like. So, okay, so this is a claim that we're going to prove, but it'll take us a while because we need to motivate the topology first. So there is a topology, let's say Txy on CTS xy for any compact Hausdorff x and arbitrary y. So, I mean, we can define a topology, and we will, on this set for any x, but it's not clear it's very interesting. I mean, it has very good properties if x is compact and Hausdorff, as we'll show. Outside of that, I'm not sure it's super interesting to think about this space. So this is the case of primary focus, and that's why we cared so much for so long about compact and Hausdorff spaces. So we're going to put a topology on that, and it's going to have the property that for any space Z, the following map this is the story over there. Well, first of all, let's agree that once if we had a topology on CTS xy, then both of these things would make sense, because for any Z, that would be a space, that's a space. I can talk about the set of continuous maps. I'm not putting a topology on that, because I'm not assuming Z cross X is compact Hausdorff, but it's at least a set. And that's a topological space, so I can talk about the set of continuous maps from Z to that. Okay, so both left and right-hand side are sets. And I can define, well, I can hope to define a map in the following way. So take in capital F, so that means capital F is a continuous map from Z cross X to Y. I want to define an element of the right-hand side. Well, it's a continuous map. In particular, it's a map. So I can try defining it by taking an element Z and sending it to, well, a continuous map from X to Y. All right? So I have to define what it does to an element X. So I have to get an element of Y out of all that input data, F, Z, and X. Well, if I've got Z, X, and F, what am I going to do? I'm just going to feed in Z and X. Now, that's a candidate definition. It may not be well defined, because for it to be well defined, the thing I get out over here needs to be continuous, and the map that I get from Z to this space needs to be continuous. So that may not be, they may not actually describe a function between those two sets. Okay, but what we're going to do is we will define a topology on CTX xy such that that map is well defined, so everything works, and a bijection. Okay, yeah.
So F here is from Z plus X to Y.
Yeah.
And so how is psi sending it to, so it, like, what is psi doing?
Yeah, maybe I should write out the ingredients. Okay, so psi Z x y of F needs to be a function from Z to CTS xy, right? So I'll define that function by saying that it's the function which sends a Z, well, it sends an element, so that whole thing, which is a function, takes an input Z and gives you a function from X to Y. Well, in order for this to make sense, I need to convince you I have defined a continuous map from X to Y. associated to f and z, and then that map is the map which sends x to the result of applying f to z and x. Okay. Yeah, so it's a bit of a mouthful, but sort of the only thing you could write down. Yeah. I mean, if you think about that example, you'll see. Okay, so what we're going to do is we're going to derive the topology itself from the fact that that needs to hold. Right? This is going to be the organizing principle for the definition of the topology on the function space. I'm going to call, because I'm going to be referring to it repeatedly, I'm going to refer to this map psi and the fact that it's claimed to be a bijection as the adjunction property. Okay, so let me be clear. So we're going to suppose, I mean, this is a common practice in mathematics, right? You want to define something, you suppose you succeeded, and then you chase the consequences until you uniquely pick out what the thing you started with had to be in order for it to work. And then you've solved the problem of making the definition. I mean, that's how complex numbers work, right? So this is a time-honored practice. So we're going to do it here. So suppose we succeeded. So suppose we have defined for all pairs x, y with x compact Hausdorff a topology Txy on CTS xy such that this map is well defined. I'll say exactly what that means in a second. And bijective. Okay, this is not fuzzy math, right? I'm adding a hypothesis. We'll see what the consequences of the hypothesis are, and then that will motivate the definition, and then we'll prove that definition actually works. Okay, so this is going to be a bit of a journey. I mean, I could write down the topology. That would be fine. I can tell you what it is in 10 seconds, and then why is it like that? Not clear, right? So this way you'll actually see why it is the way it is. That's actual information. What do I mean by psi being well defined? Well, I mean that for every continuous map F and every Z, the map that sends x to f zx is first of all a continuous map from x to y. That's a precise statement. And the function which sends z to that continuous map is continuous with the topology Txy on CTSXY. And the result of all of that, now, I mean, that's a precise statement of what I mean by psi being well defined, and that psi is a bijection. Okay. All right, so this supposition is running through the lecture. So the resulting topology is going to be called the compact open topology for reasons that you'll see. I mean, just so it's clear, making this hypothesis and then chasing its consequences will pin down what the topology has to be. That's not a proof that that's a bijection by any means, right? That means that if that holds, the topology has to be the particular thing we're going to arrive at. That's necessary but not sufficient to prove that the adjunction property holds, that is, that that's a bijection. We have to prove that separately, which we'll do. Okay, so this is called the compact open topology. All right, that's a bit of a mouthful. Are there any questions about what we're doing? And I set it up this way because getting the topology on the function space is one of the least, it's a sort of one of the non-trivial things we're going to do in this course. And it's foundational to a lot of what you'll do if you go on in functional analysis or other subjects, so it's worth paying close attention to why it is the way it is. All right. Okay, so let's just play. So we're assuming we've got this bijection psi. So let's just play with it a bit. All right, well, let's take Z to be CTS XY. Right, we're supposing we have some topology, TXY on CTS XY. So why not take Z to be that space? We can do that. So then the hypothesis tells us that we have a bijection between CTS XY with something over here. Right? So the hypothesis tells me I have some bijection here. Also, there must be something mapping on to the identity over there. So there's some continuous map, which I'm going to write EVXY. Wonder if you can guess what it is. Such that psi EVXY is the identity on CTS XY. Well, there's a unique such thing, and I know precisely what it is because I have this formula for psi, right? So if there was some f, that's my f. If there's some f which maps to the thing that I began with, the identity, then just looking at that formula, I can read off what that map has to be. It is the map which takes a pair, well, it's called EV for evaluation. Right? It takes a pair of a function and a point and just evaluates the function at a point. Okay, I could have written that function down, of course, without saying anything about psi. So what's the point of all this? The point is that the bijection tells me that's continuous. That's not automatic. Okay, so of course what this means is, given that hypothesis, this function with the topology Txy that I'm hypothesizing is continuous. All right. And that's for all compact Hausdorff X. I have such a map. So it's called the evaluation map. Okay, well, I mean, forget about this hypothesis for a second. If I just gave you three spaces, well, those are three sets, CTX, oh, I keep saying that, CTS, YZ, CTS, XY, CTS, XZ, and I can define the function which just composes, right? Take a G, which is a continuous map from Y to Z, take an F, which is a continuous map from X to Y, and output the composite, and composites of continuous maps are continuous, so that's a well-defined function. And I claim that with the topologies that I'm hypothesizing exist on all these things, right, because I have a topology for any CTS which has in the first position something compact Hausdorff, that's compact Hausdorff, so is that, and that's X again. Okay, so I have topologies on all these things, and therefore the product topology, and it could follow or not from the generic hypothesis that I've made that that thing is continuous, and it does in fact follow from that hypothesis. That's the claim. All right. Well, so let's call this C, X, Y, Z. Well, let's say it a different way. So let's start with this space. I have the evaluation map, which eats a function from x to y and an element of x and gives me an element of y. So I can look at the Cartesian product of the identity on CTS YZ with the evaluation map. That will be a function, certainly a function to that Cartesian product. And we didn't explicitly discuss this, but if you take the Cartesian product of two continuous maps, the result is continuous. Okay, that's an exercise in the notes to check. Follows from the universal property of the product, if you like, or you can check directly. So that's continuous. And then I can compose with the evaluation map for y and z. So that's, I mean, this is continuous. That's what I just showed. That follows from the hypothesis. So both of those are continuous, and therefore the composite is continuous. Okay, well, what's the point of that? Well, remember, my hypothesis is not just for a single pair. My hypothesis is that for every compact Hausdorff space and any other space, I have a topology, and this works for all triples Z, X, and Y, where X is compact Hausdorff. Okay, so now let's have a look. I've got a Cartesian product of two spaces. That one's some space, that one's compact Hausdorff, and it maps to some third space. So I'm in this situation, right? I've got a continuous map from a Cartesian product to some space, and therefore the hypothesis tells me, applying psi, I get not only a continuous, well, I get a continuous map, that's the well-defined part. Okay, so what is the image under my psi, the relevant psi? Yes, I can write out all the bits. So the image of the above under the map, which is psi, the first subscript is the z, so that's, this is kind of gross. So that's the first thing in the subscript, and then there's an x, which is x, and then there's a z. Okay, so the image of that thing, which is continuous, so it lives on the left-hand side, under psi, is a continuous map. That's the running hypothesis. And it's a continuous map that goes, well, from Z, which is I mean, this is the Z over there, right? So it goes from CTS YZ across CTX XY to CTS XZ. And well, there's a formula for it. And if you look at that formula and see what psi of that thing is, and just write it down, you'll see that it's precisely the composition map. Okay, so that's a proof from our hypothesis that that composition map is actually continuous, given these hypothesized topologies, with the property that psi is always well defined and bijective. Okay, so well, what are we doing? We're trying to derive what T, the topology, has to be. So we're setting up a whole bunch of things that have to be true given this hypothesis, and then we'll derive from these facts that certain things are in the topology. Okay. Right, so the various partial functions are also continuous. Partial functions, I mean, has the usual meaning, right? If I have a function of two inputs, which that is, and I fix one of them, then the resulting thing is a partial function. So if I take that continuous composition map and I fix the thing which lives in the second variable, that is a continuous map from x to y, then I get a continuous map again. And that continuous map is pre-composition with f, right? So it sends a continuous map from y to z to a continuous map from x to z. So that's continuous, and so is the other partial function. So g is from y to z, then fixing the other variable, I get a continuous map from x, y to x, z, which is post-composition with g. I'm going to write that G circle blank, right? So this is an indication. It just takes an input and composes it with G. So this is continuous as well. All right. Okay, so here's the crucial trick, and what explains the revenge of Sierpinski remark. So let X be compact Hausdorff. Okay, so I'm supposing I've defined a topology on CTS X, Y for every Y. That includes the Sierpinski space. So this hypothesis includes some topology, Tx sigma, on this set of continuous maps from X to sigma. All right, and I claim that it follows from what we've done that the singleton consisting of just the characteristic function of X is an open subset of that space. So remember that if U in X is open, the characteristic function of U, that's the map from X to sigma. Remember sigma was 0, 1. The characteristic function sends everything in U to 1 and everything outside U to 0. So this is the function that sends everything to 1. Okay. And that's continuous. That's something we checked when we defined the Sierpinski space. So that's an element there, and the singleton is open. That's the claim. All right, so this is a little interesting. Okay, it's not meant to be clear what the hell that has to do with anything at the moment. Okay, but this will tell us what the topology is in a second. Okay, so take the projection map from the Cartesian product that's written there to the first coordinate. Let's call that pi 1. Now, projection maps are always open. That is, they send open subsets of the product to open subsets of the factor. That's easy. They're not always closed, but if the thing that you're getting rid of in the projection is compact, that projection is closed. So I've left that as an exercise, but that's one of the exercises I will provide a solution to in a couple of weeks. Okay, so that's an important fact. All right, so that's a closed map. It sends closed sets to closed sets as a result of X being compact. All right, well, and the evaluation map is continuous. Right, we just showed that. So that means that the pre-image of any closed set here is closed there, and then I can apply the projection to it to get a closed subset of CTSX sigma. Right, so EV X sigma, well, I mean, the singleton 1 is open in the Sierpinski space, so the singleton 0 is closed. So the pre-image is closed in that Cartesian product, and therefore the projection, the image of that guy, is closed in CTS X sigma. Well, what good is that? Well, it's the complement of this singleton, as we're about to show. So that's the end of the proof. Okay, so let's just examine what functions from X to sigma lie in that image. Let's give this a name. I don't know. Q maybe. Right, so that's some closed subset of this space. Now, every continuous map from X to sigma is the characteristic function of some open subset. So I'm allowed to do this. So chi of V, V in X open, is in the image. If and only if there exists, well, if it's in the image of pi 1, that means there exists some pair that maps onto it. Well, it itself is the first component of that pair, so that's exactly to say that there exists some X in X such that the pair chi V comma X lies in the pre-image of 0. that says that there exists an x in X such that the evaluation map applied to that pair, well, lies in the singleton 0, which is just to say that that's 0. But that says that V is proper, right? Because it says precisely that there exists an x in X such that applying that to that gives 0. But chi V is the characteristic function of V, so chi V x being 0 says that X is not in V. All right, so that says V is proper. In other words, the set Q that we found is precisely the set of characteristic functions for V, a proper open subset of X. So the complement is just a characteristic function of those open sets which are not proper, but there's only one of those. It's the whole space. So Q is closed, so the complement is open. Okay, so that's it. All right. So, yeah.
What's x sub u or x sub v?
Yeah, that's a chi. So, given u in X open, chi u is the function which sends an x to 0 if X is not in u, 1 otherwise, that is, if X is in u. So we checked in some lemma that the continuous maps from X to sigma are precisely the characteristic functions of open subsets of X. Okay. All right, so here's finally where we arrive at the characterization of this topology. Oh, yeah.
Just quickly, what does proper mean?
Oh, proper just means it's so a subset of a set X is proper if it's not the whole thing. Yeah. All right, so lemma. I mean, if it's the 2-point space with the discrete topology, then that's just saying, I mean, that parameterizes disjoint open subsets whose union is X. That's not really playing the relevant role. Yeah. So X is compact Hausdorff. And Y is arbitrary. Then for K in X compact, well, I could have just said closed, right? Any closed subset of a compact space is compact, and any closed subset of a compact subset of a Hausdorff space is closed. So having K in X compact is the same as having it closed. I say it this way because we call it the compact open topology, because we're sometimes defining it on spaces which aren't necessarily compact Hausdorff. Okay, so I could have just said closed. And for U in Y open, the following set, SKU, which is all those continuous maps from X to Y, such that F sends K into U. So that's a set of functions, and I claim it's open in the topology on CTS XY. So just to remind you, we just hypothesized that there was some topology chosen simultaneously on all these spaces, these mapping spaces, which made the adjunction property hold. And any such topology must include these particular open sets, okay, parameterized by K and U. And we'll just take the smallest such topology and then show that it works, and that's the topology we want. Okay? So this generates the compact open topology. That is to say that SKU belongs to TXY. All right, so the inclusion F is continuous. And well, as a subspace of a Hausdorff space, X is Hausdorff. So K is one of the things I'm allowed to talk about as the first position, in the first position of one of these CTS spaces. And if I take the characteristic function of the open set U, that's a continuous map from Y to the Sierpinski space. Okay, so so this is the map that precomposes with F. Right? Take a continuous map from X to Y and, well, restrict it to K. That's what it means to precompose with the inclusion. That's continuous because that's this thing here, right? This was continuous as long as those two things were compact Hausdorff, and they are. So that's a continuous map. So that's continuous. This map here is post-composition with G. And that's also continuous by what we discussed. So that whole thing is continuous. All right. So now let's compute the preimage. Okay, and the singleton consisting of the characteristic function of Y is open in CTS Y sigma. Right? That's this. So the following subset of CTS XY is open. There's all the H's. So I'm just going to take the preimage, take the right. The characteristic function on K is an open subset of that final space. That's a continuous map. Take the preimage of that open set. That's an open subset of CTS XY. Which open subset? Well, it's all those H's whose image is in that singleton, and the image is just where I take G, circle H, circle F. To be in that singleton is just to say that it's equal to psi K, chi, K. Well, what does that say? It's the H's such that chi of U, circle H, circle F is equal to chi K. That's just the inclusion of K into X, right? So that's just all the continuous maps such that chi U of H of K equals chi K of K for all K in K. Okay, but that's 1 always. So that's just the continuous maps H such that chi U H of K equals 1 for all K. All right, which is precisely those H such that H of K is in U for all K in K. So that's all the continuous maps that send K into U. So that's open. And so we're going to have to stop there, but that is the compact open topology. Take the topology on CTS XY, which is all unions of finite intersections of such things. That's the smallest topology containing the SKUs. And that topology we'll prove has the adjunction property and makes everything I just said all work. So no more hypotheses, it'll be actual fact.